All right, hello and welcome. So this is some more symmetry stuff. I think you probably sent us theme, probably based on all the things that I've posted. Um, this is this was a something I was thinking about in terms of polynomial functions. So if you have a function, a polynomial function, or any function really, and its inverse, it's symmetric about this line y equals x. So my question was, what polynomial functions are their own inverses? So that is to say, which functions are actually symmetric about this line. Um, so as it turns out, the only functions that are their own inverses, only polynomial functions, I should say, that are their own inverses are the linear functions, and they're one of two types. The first type is this kind of line, negative x plus b. So it's actually perpendicular to this line y equals x. So they're just all these parallel lines, just different points based on whatever that b is. So it'll just shift it up or down. Um, and the function f of x is x. So that's just the identity, which would just be the line itself, okay, which is clearly symmetric about itself. So those are the only two possibilities that you can have for any polynomial. And for a while, I was thinking about it very geometrically. I was kind of focusing here when you could actually focus on the algebra, and that will actually guide you and uh, show you what the result is. So this is what I came up with this result. So if you have a polynomial, uh, its composition with itself is the identity, if and only if it's one of these two types, either the identity line, so just y equals x, or y equals negative x plus b. It's got to be one of those two. And it's an if and only if, so kind of goes back and forth. Okay, so those two are equivalent. So to prove that, and this is where a lot of the work came in, but it's pretty straightforward. When I was focusing on the symmetry side over here, just the geometry, it kind of restricted my thinking, and I couldn't really see what to do. So this is what really kind of broke through. So you start with this, okay? So going in the first direction, assume this is true, and then you can show that's true. So first, suppose the composition is the identity, and this was the key part, is looking at the degrees of the two sides. So if these two are equal for all x, they're both polynomials and they're equal, that means that their degrees must be the same. So this is the result that really helped me. So the degree of the composition, f composed with f, is equal to the degree of the identity, which is just 1. Okay, so the degree of f composed with f is 1, and the result you need here, the degree of f composed with f, is degree of f times the degree of f. Okay, and there's a more general result, degree of f composed with g, the two polynomials, is the product of their degrees. So that's exactly what we have here. Degree of f composed with f is 1. That means the degree of f squared is 1. And since this is non-negative, it's got to be equal to 1. Okay, it's an integer. So the only way that this can be true is that if the degree is 1. So that means that it's linear. Okay, so therefore f must be some linear polynomial. So it's ax plus b for some numbers a and b. Okay, so we have that. And then coming back to this original equation here, f composed with f is the identity. You plug in those values, so compose f with itself. You get a times f of x, which is ax plus b equals x. Okay, so just substitute in those values and then distribute the a through a squared, x plus ab plus b equals x. And again, these are all for all x, okay, throughout here. And then, so then we can get the x's to one side. Okay, so you have a squared minus 1 times x plus a plus 1 times b is 0. This is for all x again. And we can factor this, a squared minus 1, a plus 1, a minus 1. So that's just a difference of squares. So you can factor those. Now you can condition on whether a is -1 or not. Okay, so if a is -1, both of these are 0, and it's true for all x. So, and you're pretty much done there. So if a is -1, then f of x is -x plus b. That's the first case there. If it's not equal to -1, that means that these are non-zero, and so you can divide, and you just have a minus 1 times x plus b equals 0. You have that simple equation, again, for all x. The only way that a polynomial like that can be equal for all x is if their corresponding coefficients are equal. So if you equate coefficients here, that must be 0, that must be 0, which means a is 1, b is 0, which means f of x is just x. Okay, so just plug in 1 for a, 0 for b, f of x is x. Okay, so that's going in the first direction. If you have this is true, then you get those. Going in the other direction is pretty easy. If you have either one of these, you compose it with itself, and you get the identity. That's all you have to do here. So if f of x is -x plus b, you compose it with itself. You get negative f of x plus b. So it's negative x plus b. Distribute the negative, so you get x minus b plus b. So you just get x, the identity. And if f of x is x, then certainly if you compose it with itself, you just get x too. Okay, so that's a little bit about that. Again, started in one area, and this is the beautiful thing about math. You kind of start with one kind of idea, and then it kind of develops into something else, or you discover something else, which I saw here, that morphs into something else, or you solve some kind of a different problem to kind of get to your solution. That's really what I like about math, that it can go down different paths, and you can kind of see which way, and maybe you figure out something else that's a little more interesting. So anyways, I wanted to share that. That's kind of a neat thing, and it doesn't require a whole lot. A lot of the stuff that I have been presenting required like some calculus, so this is more like maybe pre-calculus type stuff. So anyways, I hope you all enjoyed it, and I will post more, and let me know if you have any questions or anything. I love talking about this stuff. So thank you, and I'll